Hello, everyone. We are Team Ernest and Duan. We're presenting our project on predicting California car accident severity. So we're going to introduce the problem and then introduce the data set that we're using, also any findings from the model. And lastly, we're going to propose some future applications and also discuss the business values and the fairness of this model and the project. So our problem here is that we want to predict whether a location in California will have a severe car accident. And here, the severity is based on the impact on traffic, and we think it's very important and interesting because there are already plenty of models that study the impact on health and public safety. So if we can know the impact on traffic, we can add some values for businesses such as traffic applications or insurance companies. And also we can help city planning or EMTs to provide more efficient services so we can reduce the economic loss due to the traffic conditions. And the last one is this is more convenient for individuals like us. So the objectives here is that we want to study the causes of car accidents and also to predict accident severities. We're using the data set, the US car accident data set, which has 1.5 million car accidents in the United States from 2016 to 2020. The data set also contains 47 features. So the Y features that we're predicting here is the severity, which like we said is based on the impact on traffic. It has value 1 being the lowest to value 4 being the highest. The other features are mainly from 4 categories. The first one is time. So we have the timestamps of the accidents. We also have some weather features. So we have categorical features that describes if a place is snowing or if it's hailing, if it's sunny. We have some continuous values for pressure, temperature, precipitations as well, etc. The third one is location. So we have the latitude and longitude of the longitude of the accidents. So they're very detailed, very clean. We have some street names of the accident as well. The last one is point of interest, which describes the traffic condition at the accident site. So if it has a stop sign or if it's a roundabout. Okay, so moving on to the right, we can also see the data set contains some missing values. So for example, the one at the very top is missing about 70% of its values. So there's no way that we can't use this feature. So we're just going to drop this feature completely. Those ones on the bottom are missing relatively low, only less than 1% of its features. So we're simply going to remove the missing rows. And then we're going to try to impute values for the features in the middle here. Last step is to clean the data types.
So after we preprocess of data, we did some like a preliminary analysis and we find some patterns which can let us redefine the scope of the problem, that is choosing California as a research object and choosing a specific time span. So first, why we choose California? So here is the map of the accident frequencies based on the counties in the United States. Darker shades means more severe accidents. California has a high number of accident counts, so we want to focus on it because like other places do not have like sufficient data to learn. And moreover, like weather conditions can be different, such as like California does not snow and it may like have different traffic policies than elsewhere. The third reason is that since there are like many severe accidents, there will be like a high demand to reduce the accident. So we want to analyze it. Second, why we want to choose this time span. So we plot the accident frequency across time, and we see that there is an M shape recently after July 2020. It may be because of the COVID, but like we see high variance at this period. Moreover, like before 2018, it will be like 4 years ago, which is a little bit outdated. To ensure that our data set is valid and stable, we choose data from July 2018 to July 2020. And now we have the data set to analyze, and we start with the EDA. First, we look at the severity. The severity is our dependent variable. And right now we have the challenges in that we do not know the clear definition of severity. And we just know that 1 being the lowest and 4 the highest. So we calculate the medians of the distance and duration in minutes at each severity level. And we see that severity 1 has a little impact, and severity 2 and 3 has similar impacts, and the 4 has a largest impact. So to simplify our analysis, we drop the severity 1 data, which also just have a few like data points. And then we combine the 2 and 3 as less severe, and we're taking 4 as a more severe. And after that, we find that our current class is very imbalanced, where 99% are less severe. So we did some resampling by SMOTE method by oversampling the minority about like 5 times and undersampling the majority to be equal to the minority. After that, we start to look at the features. We start to look at the time features. We first, our problem is that our problem is not a time series problem. So we want to consider some time features as the causes of the severe accidents. By now, we only have a feature timestamp. So we manually classify time into days, hours, and weeks. On the left, we see more accidents during the weekdays. So we have the feature week or not. On the right, we notice that there are more accidents during the days, but like there are more severe ones at night. So we change the features into day or night. And then we look at the week features. Here we observe some patterns on seasons and holidays. Spring and summer has more severe accidents, and like Thanksgiving has fewer severe accidents. And now it is worth noticing that right now week is a nominal feature, and we want to change it into categorical feature based on the patterns. But we face the challenge that some patterns are hard to measure. So such as like, how do we measure the impact of holidays? Has Thanksgiving has the same impact as July 4th? And can we interpret all the patterns? So instead of that, we decided to choose a tree-based model later, which does not care about nominal or ordinal features, and the model can learn to summarize the pattern itself. And now we look at the weather features. So in weather features, we still need to deal with some missing values. So we first impute those values by filling from same city in the same week. For categorical features, we fill with mode, and for continuous features, we fill with the median. And then we did some like text engineering. One weather indicator in our data set is weather condition, which is a categorical variable with over 100 labels. So we applied text manipulation to sort the labels into 6 groups, and we noticed some patterns that like severe accidents are more likely to happen on cloudy days. And we can see from the charts that California has really good weather compared to Ithaca.
All right, so now that we've come down to 20 features, we will fit 4 models. And the first one that we use is a logistic regression model. This is because it is the most classic one for a binary classification problem like this. So we've standardized the features, we've used regularization in lasso, and we actually used a grid search to find the best hyperparameters, and we use cross-validation to avoid overfitting. However, logistic regression still gives us a poor performance, only about 60% of accuracy in both classes. So this indicates that there's non-linearity in the data set, and which is why we want to use a tree-based model next. So we use the random forest model, which is tree-based method. Like we said, it doesn't care about whether it's nominal or ordinal features. It's ensemble learning, so it's more robust, and it helps us choose the features. And in fact, random forest this way really improved the performances. So now we have a 97% of accuracy, and based on the chart on the right, which is the feature importance, we can see that those features on the bottom doesn't have a lot of importance, so we can probably get rid of them later. The ones that are important here on the very top, the first one is week, then is the longitude and the latitude of the location, and we have some 2 weather features, the pressure and the humidity. So next, we are going to build a random forest model using only these 5 features, and that's what we did here. And this model gives us a similar performance, it's a relatively good performance as well. It's about 96%, very close to what we had before. So that means the 5 features from these 3 categories can explain most of the variance in the data. The last model that we tried is a control bird. So this is similar to random forest in terms of growing trees and in terms of its ensemble learning. But control bird can further choose the features using regularization, and we see the result from the right. So here, no matter how we fit this model, we always choose week as the most important feature. So this confirmed what we've seen before in random forest. But in control bird, if we want to select fewer features, it compromises the accuracy. And if we want to ensure the accuracy, then it'll probably choose most or all of the features. So in general, random forest with 5 features is considered the best feature, the best model in our analysis. So we're going to compare these models. We're first going to see the accuracy in terms of the 3 metrics here. Random forest has one of the best accuracy there. And in terms of interpretability, it uses only 5 features. So it's easier to interpret. And we are confident about this result because we prevented the overfitting or underfitting issues. We used 20 features, fewer features with enough observations. Features are from different perspectives, and we dropped the ones that has no value. And we tried validation and cross-validation test sets and tree-based method just to ensure these. Okay, so next we're going to apply this model to predict accident severity in LA on a synthetic data set. So this serves as a demo of how we're going to apply this model later. So first, the model has three kinds of features, weak features. We can generate weekly forecast. So here in the demo, we're just going to use week number 27. For coordinates, we can input any coordinates. So in the demo, we've generated the uniform grid of coordinates in LA, which is shown on the right. Or we can use coordinates from the existing data set, which is shown on the left. Next, we can also take inputs from weather forecasts. Here, we're just going to use historical median values here now. So this is our results from accident predictions, and we're going to start from the right. So we see that downtown LA may have more severe accidents than other places. And if we plot fewer points, we're going to have a clearer map. So we see on the left here, West Hollywood and Beverly Hills may also have more severe cases than other places, and not so much in Santa Monica. So next, we've also proposed 3 potential use cases for this model in this project. So the first one is for the general public. We can create these traffic apps. So these traffic applications can predict if a place is going to have a severe accident, and then it can tell its users to avoid accident frequent zones, such as here in downtown LA. So this is a commercial use, and they can add profit to these software companies, and it would be more convenience. It brings convenience for users. The next one is for insurance companies, that they can adjust their premium based on where and when it's more likely to have severe accidents. For example, from our analysis here, San Francisco, San Jose, and Los Angeles going to have more severe accidents, so their premium may be a little higher than other places. So this is for another company, it's a commercial use, and we help this company to make decisions in a data-driven manner. The last one is for public services. So first, we can prepare them for these accidents. For example, we see on this graph, downtown LA is going to have more, so because it has more red dots here. For any EMTs can try to avoid this area when they're on this urgent duty, when they want to go to somewhere else, just to avoid the traffic. And also, we can try to prevent these accidents from happening, because here, as we see, this is a freeway exit, and we see that it's going to have a more severe accident here. So we can probably put up some signs and warnings just to tell drivers to drive more carefully. And we can increase the efficiency and reduce any economic loss due to the traffic. And that's our goal and the values that we want to achieve here.
And now, as we consider limits and fairness of our model, we concluded that our model is objective and fair. For the fairness, since our dataset contains no driver information, so there will be no discrimination based on age, gender, race, or health conditions. Moreover, all of our features like weather, locations, or time are very objective, so like our model is pretty fair. For weapon of mass destructions, although our model has some drawbacks, which would be like a pretty similar to weather forecast, it is not a WMD. First, our outcome is not hard to measure. The accidents data are collected constantly, and the new data could be used to justify and modify our current model. Second, our prediction does not generate negative consequences. Of course, there will be like a risk since the accuracy is not like 100%, but even the input weather forecast can be wrong. So it is very reasonable. Moreover, since our inputs are objective, the results cannot affect the next round input. So there will be no like feedback loops. So that will be like all our sharings. So thanks for listening.
Thank you.